Okay, welcome. So what we're going to be doing is we're going to be going over the next couple of topics in energy. Basically, this is going to cover potential energy and I'll get into power as well today. The main thing I want to do is go over potential energy and mechanical energy. We'll define both of those. They're related. But first, I want to just kind of review a little bit of what we talked about yesterday, or in the previous lecture, rather. And so I've got these three sort of example questions to start off with. Now, this is just kind of just a review about work. And there's a couple of different ways you can think about this. So the first one, a guy is holding a box at 2 hours for 2 hours as he stands still. How much work does he do? Well, hopefully, if you remember what work means, there's a couple ways you could attack this, but there would be 0 joules of work done on this. And the reason for that is the box isn't moving. Delta X is 0. Okay. Now, really, if we were to think about this, we would say, okay, that's not quite right. Like he's probably not holding it perfectly stationary. So if we were to do a really fine-grained analysis, we could talk about how much work he's actually doing. But the box is not having its kinetic energy change. So the work that this man is doing as he's not displacing the box isn't being displaced. He's not adding or removing energy from the system, so he's not doing any work. Now, in this case, the delta x does not equal 0. The second case, the delta x does not equal 0. It does not equal 0. It's 1,000 meters. 50 kilogram box. It's over 100 pounds. It's quite a heavy box, and he's doing it. He does this for 2 hours. It's a long time to take to walk 1 kilometer. But this time, how much work does he do in the box? And it may surprise you to know that it's actually still 0. Okay. And the reason is that his force applied is up. Okay. Now, you might argue, well, he's got to have some sort of force applied to move the thing forward. But if he's doing this at a roughly constant velocity, as we understand, there's no real force that's required to do that. Now, strictly speaking, if you were to go into a fine-grained, detailed analysis of the biomechanics, he would do some work. But as we understand it, his force is up, his delta x is right. This force is not in the same direction as the delta x, so it can't add or subtract energy. The other thing is that the box's kinetic energy ultimately doesn't change. Now we might be curious about that. Maybe he's speeding up, adding energy to the box that way, but for the most part, the box's kinetic energy doesn't change, so it didn't have any work done on it. Okay, so that's something to keep in mind. Now, for the last one, he lift the box 2 meters. So his F applied will equal weight of the box. Okay. So that's basically what he's going to do. And we're going to say that's around 500 newtons, just 50 times 10. That's fine. And then delta Y in this case, because it's vertical, would be 200 meters. So that's also up. So that would be 200, 2. So we'd have 500 times 2 would equal 1,000 joules of work. Okay, so hopefully you can kind of see the distinction here between having just exerting a force and doing work. That's kind of what these questions are made to distinguish between. So send me an email if you don't understand these, or just ask me a question some other way. Okay. So next thing I want to talk about is I want to revisit this work on versus work by. So work on, as a reminder, this is all forces. Okay. So it's all the relevant forces that might change the energy of a particular object. Now, work by, and that's really what we're going to be dealing with today. This is from a single force. Okay. And the idea here is that what we want to look at, and the reason I'm going to do this is that some forces, let's say when work is done against them, effectively is done, we'll say against them. Effectively store that work. Effectively store that work. Now, the general name for this is called conservative forces. And the reason they're called conservative forces is basically work can be done to an object, and that in general work increases the energy of an object. Now, if you've got a force, working against you, then that might cancel out that energy. The classic example is with friction, where you can push a box and you're putting energy into that push, you're doing work on the box, but friction is basically doing work against you, keeping you from increasing the kinetic energy of the box. So you might push it and it might stop immediately. So even though you spent some energy, friction basically took that energy right out. Another example you can have of this, and this is an example of a force that stores work, is gravity. Okay, so the idea here is, and this goes to what we were just talking about. If you lift a box against gravity at constant speed, all right. Now, basically, what this means is what you would have is you'd have your applied force that you are applying to lift the box. You'd have the force of gravity, and because it's a constant speed, there's no acceleration. These things are going to be counter to one another. Now, the idea is that gravity prevents the energy you add from increasing the kinetic energy. Okay. And so in this case, from increasing the kinetic energy. So we'll just say, for the sake of argument, it's 10 meters kinetic energy. So we'll just say, delta Y was 10 meters here. The work done by your applied force would be the applied force times 10. Okay. But the problem is that you didn't increase the you didn't increase the energy, so your net work is still zero. Okay. And that's the combination because, and again, the whole reason for this is that your F net was zero. All right. Now, the work done by gravity is actually going to be negative FG because it's going in the opposite direction of the delta Y times 10. And this kind of makes sense is that if the work you add is equal to the work that gravity removes, then basically your net work is going to be zero. But the point with this is that once the box is lifted, gravity can give back, and I'll put this in quotes loosely, it gives back the energy you spent against it. Okay, and the idea here is that now if you drop that box, gravity will now do positive work on the box because the box will go downward. Gravity, the force of gravity is acting downward, and all the energy you spent to lift it, gravity is now going to turn into kinetic energy. Okay, so we call this storing of work done against these kinds of conservative forces. So work done against conservative forces is stored in what we call potential energy. And really, all we mean by potential energy, the potential energy, really, it's just potential work that a conservative force could do. All right. So if you've thought about, could do. So if you've thought about gravity and, if you've seen the formula for gravitational potential energy, I'll use the symbol U for gravitational potential energy. U sub G, G being gravitational. It would just be the force of gravity times the delta Y. Okay. So it's the force of gravity times the delta Y that you have lifted. Now the idea is that if the work done by gravity, the work done by gravity would be that force of gravity times negative delta Y. Well, we'll just say delta Y just for and again, it's the f sub g multiplied by the distance, we'll say the vertical distance it moved. Okay. And this is the idea, is that if an object is up at some height, and this is another way you'll also see this one, mgh is the way you'll see it written, where again, h is equal to delta y in this case. If an object is up at some height, gravity can potentially do the work, bringing that object down to that height. Now, what's really interesting about this is it doesn't matter the path that it takes. Okay, gravity can do the same amount of work no matter which path the object takes. So if it goes down a slide, gravity does the same amount of work. If it slides down a ramp, gravity does the same amount of work. If it goes up and then down, gravity does the same amount of work. Okay, so the idea here is that gravity will do work based on the height that an object is located at. Now, this is going to depend on where your 0 point is. So it takes a little bit of, this is a topic that generally gets a little bit more practice if there's more time. But it takes a little bit of, but it does, you do get to define your 0 point. So potential energies can be positive or negative depending on what your height equals 0 point is defined as. What is often more relevant is a change in potential energy than an absolute potential energy. Okay, so using a particular reference point, you'll often be looking for changes in potential energy as opposed to overall potential energies. So the two potential energies to know. One is gravity. And the idea is, so U sub G, and that's just equal to mgh. You'll often see me do this as mg delta y. And the reason I do that is because it relates it back to the kinematics quantities. And that delta y is, it's helpful if the object is not just moving in a single direction, but moving in multiple directions. So it's moving in the x and y direction. You can still write its gravitational potential energy as the overall change in delta y. Now, again, this is that more has to do with the change in gravitational potential, but we'll leave that alone for now. Now the other one is the spring potential energy. So this is gravitational. And the idea is that with the springs we were talking about, you kind of imagine a spring doing the same thing. You push against a spring, like you push to compress a spring, and basically what the spring is doing, it's storing the work that you did against that spring that it can push back out. And it turns out that that this is another form of potential energy that we can look at. Now, figuring out the work done by the spring. With gravity, it's pretty easy because it's just the force of gravity times the direction the thing moves. And since they're both down and gravity's constant, it's no big deal. But the spring force varies. So the idea is that the further you compress the spring, the harder it's going to push. So as the spring starts expending energy, it doesn't push as hard, which means it doesn't move as much. So I'm not going to go through the derivation, but the spring potential energy is 1/2 K, where K is the spring constant, delta X squared. Now, this is spring potential energy. Now, as a reminder, the spring force was just equal to K delta X. So the idea here is if we can't just do K times delta K, we can't just do the spring force times delta X. And the reason for that is that as delta X changes, the force changes, which means that is not a constant force. And that's where that 1/2 factor comes in. Basically, what you do is you do the average force over the delta X, which is, half the maximum force is the idea. So that's basically how spring potential energy will work. Okay. Now when we talk about so those are the two conservative forces that I think is going to be most important for us to know. When we talk about non-conservative forces, another way to think about these conservative forces. Another way to think about these is these are basically forces that that either dissipate kinetic energy or in some cases they can add. So we'll say or add, and I'll say unstored kinetic energy. The idea is that another way you can think about it is that gravitational energy and spring energy will effectively store kinetic energy. So the idea there is that you toss a ball up into the air, it has kinetic energy at the bottom. That kinetic energy gets stored in gravitational energy up to the very top. And then, it is all gravitational energy when it gets to the top. And then it starts getting converted back to kinetic energy. Okay. Now there are forces that will add kinetic energy, but it's not stored kinetic energy. So an example of this would be like someone pushing it, where you could add kinetic energy to a system, but that's not being stored anywhere mechanically. You could argue it's being stored in the chemicals of his muscles, which okay, fine. But that takes that's going to mean a broader perspective on energy that we're not taking here. We're just focused on the mechanics of the system. Okay, so dissipative examples, dissipative forces. These would be like friction is going to be the main one, but also drag. And the idea is that these effectively remove kinetic energy. That is basically their function. Okay. Now, as a consequence, they remove what we'll talk about in a minute. They remove all mechanical energy. And again, mechanical energy is something we'll get into in a minute. But something that could be additive would be like an applied force, where again, like I was saying, you add kinetic energy to the system, but and the net effect is that increases the overall mechanical energy of the system. So I want to define that term now, mechanical energy. And basically what mechanical energy is, this is a combination of kinetic and potential energies. All right. And the reason we do this is because in our study of mechanics, we are often interested in converting between kinetic and potential energy. All right. And so in order to do that more effectively, we define a new category where the mechanical energy is effectively equal to K, the kinetic energy, plus I'll use the gravitational energy plus the spring energy. Now, there's also electrical potential energy, which is another form of mechanical energy. We're not really going to get into that. Definitely not right now. Probably not even when we cover electricity. But that is the idea. Now, in the next lecture, we'll get into conservation of mechanical energy and how this is relevant. But this is the main thing to know, is that this category is something we're going to be when you're looking at energy conversions in this particular class, you're going to be looking at energy conversions between kinetic energy, gravitational energy, and spring energy. Okay, that is basically what you're going to do. So an example of this, when you're doing this, if you had like a bobbing spring, say. Now we'll do three different situations: one, two, and three. All right. So if you the first thing you do if you want to get the spring bobbing, you extend it downward. Okay. And you've pulled this thing downward. This is the delta Y that you've pulled it. So you've pulled it downward. Now, what kind of energy do you have in here? See if you can answer that. Now, you're holding it stationary at this point. You haven't let it go yet. So no kinetic. So we'd say kinetic equals 0. Now, we would also probably say, I would probably say that this is as low as the thing is going to get. Okay. So it's not moving. It's also put it this way, it's the lowest height that the thing is going to attain. Okay. So we could do this a couple of different ways. We could say that the gravitational potential is 0 here, or we could say that it's negative because it has gone down. Now that's a matter of where you define your 0 point. So sometimes people like to define the 0 point at the lowest point. Sometimes that's convenient. Sometimes it's more easy to define it at the equilibrium point. So where this thing would hang just normally. Like that's another common place to define 0 potential energy. I'll do it. I'll just say the potential energy is I'll just say it's less than 0. So it's equal to mg times negative delta y. And again, the idea is that the delta y went down. Okay. So we removed potential energy by forcing this thing to go downward and not letting gravity accelerate it downward. That's basically what we did. And then the spring potential energy would be equal to 1/2 k delta y squared, whatever that happens to be. Okay. So now the spring is, now we let it go. And what we do is we go down. I'll draw the equilibrium point. And now the thing starts moving back up. And now it's here. Quite do that. And now it's here. Okay. So it's now moved up. And as it goes back through its original point, it has some velocity. Okay. So now I would say my K, drop this down here. So now I would say my K equals 1/2 mv squared. And I would say my u sub g is now 0. So this was my 0 point. I could call this y equals 0. So my u sub g is now 0. That's what I'm defining as height equal to 0. And then the spring is also at its equilibrium point. So u sub spring is now equal to 0 as well. And then what will happen is this thing will, bob up, and it will compress the spring until it eventually stops. And at which point we'll just call this delta y3. Well, it's now stopped. That's the stop point. So my kinetic energy is now 0. And my gravitational potential energy is now mg delta y, because now it's above its equilibrium point. Now gravity could do some actual work pulling this thing back down. But interestingly enough, we also have some spring potential energy again. So this, hopefully. So I'll do K sub spring. And so U sub spring is equal to 1/2 K sub spring delta Y squared. Delta Y. It's in the third step. Okay. So basically the idea here is that that you've converted between different types of energy. And this is somewhat common in mechanical systems, that you convert between these types of energy. Okay. So that's why mechanical energy is a relevant idea for what we're talking about here. All right. And we'll get more into that when we talk about conservation of energy in the next lecture, which is what the next lecture will be on. Okay, I wanted to look at a couple of examples just with gravity, just to hopefully help you sort of get this idea behind what we're going to be looking at here. Now, what we have here is a couple of problems. I'll give myself some space to do this. Okay, so it says, how much work does gravity do? How much work does gravity do when we drop a 1 kilogram object off a cliff of 10 meters? Well, basically, what you're going to have is your delta y is going to be, we could just, if we want to, we could make down positive. I'll leave down negative. So delta y is negative 10. It goes down 10 meters. And then your FG is also down. So that is equal to mg. So FG will also be 1 times 10, but it's negative, so it's down. Okay, so how much work does the gravity do? Well, the work of gravity is equal to Fg times delta y, which would be equal to negative 10 times negative 10, which would be 100 joules. Well, notice that this is exactly equal to U sub g, which is mgh. Okay, so that is exactly equal to that because, again, F sub gravity is mg. So basically the work done by gravity was equal to its initial potential energy. Okay. Now, how much work does gravity do when we lift the object back to the top of the cliff of a height of 10 meters by a rope? So this time, and this is what's interesting, this is why it's helpful to do that. The work done by gravity is still Fg delta y. And Fg hasn't changed. It's still negative 10, but this time delta y is equal to 10. So gravity this time actually does negative 100 joules of work. And this is the whole reason that you need a force to lift this thing up, but you lift it without it increasing its kinetic energy. It's still basically not, it doesn't really have a velocity when it gets to the top because gravity was taking the energy out of the system as soon as you could do it. So in this case, when you lifted it, gravity did negative work, but this negative 100 joules then gets stored as 100 joules of U sub g. So 100 joules of potential energy. All right. Now, how much work does gravity do when we throw the 1 kilogram object off a 10-meter cliff with an initial vertical velocity of 2 meters per second? So now basically what we have is we have this right here. And now people might say, oh, well, crud, I don't know. It goes up and then down. Do I need to find out how high it goes up? Well, it turns out that this, whatever it goes up, is going to be, is the negative work that gravity does when it goes up is going to be canceled by the work that gravity does when it starts coming back down. Okay, so basically the two works in this region cancel out. So the only work we have to realize for gravity is just the force of gravity, which again was negative 10 times the negative 10 meters since it's going down. So my work of gravity is still 100 joules, which again was just equal to the mgh, to the gravitational potential energy it had sitting at the top of the cliff. Now, in the case of when you throw it as opposed to just drop it, you also give it another form of energy. So think about which other form of energy you give it at that point. It's kinetic, but similar sort of thing is going to happen in this last one. What we have here is still delta y is equal to negative 10. Now, again, what the thing is doing is it's doing kind of like this, like so. And so, you have to worry about, okay, it goes up and then it comes down and it's also going horizontally. Well, first of all, FG does no work horizontally. So you don't even need to worry about the horizontal distance. okay, when you're calculating work done by gravity. All right, gravity is not going to do any work horizontally. And again, we know this from projectile motion. Gravity does not increase the horizontal component of the velocity. So it's not going to increase the horizontal addition to kinetic energy in any way. Okay. And then the up and down will still be canceled. So really, it's still just going to be FG delta Y. And that will be the work done by gravity. So it's still just negative 10 of newtons times negative 10 meters, which is going to give you 100 joules that gravity, 100 joules of work. That should have been a J there as well. Okay, so the point here is that no matter what, because gravity is only acting down, and so we only care about the downward displacement, and because it does negative work when something goes up and then positive work when it goes back down, it doesn't matter the path that this thing takes to get from the top of the cliff to the bottom. Gravity will always, always, always do the same amount of work, and that is why we categorize it as a potential energy. Because gravity, however this thing gets down, assuming there's not some dissipative force, and you could argue drag dissipates a little bit of the energy, and that's true. But another example of a dissipative force would be if you lowered it slowly. If you prevented gravity from doing the work, that would be another example of dissipating some of the energy. But if that doesn't happen, gravity will always add the same amount of energy to this system. So I hope that makes sense. Last, I do want to do one more example with this just to show you kind of how this works. So this will be a longer one. Okay. All right. So here are some of the symbols that end up getting used, and it changes from book to book. But it says here, a 0.21 kilogram apple falls from a tree to the ground 4 meters below. Ignoring air resistance, determine the gravitational kinetic energy, kinetic energy, and total mechanical energy when its height is above the ground. Take each of the following. The ground level may be a point of zero potential energy. So the idea here is I'm not going to bother to draw the tree, but what we're looking for is we have y equals 0 down here. Our initial case, it's at 4 meters and velocity equals 0. Our middle case, it's at 2 meters and we don't know what our velocity is. And our last case, and then again, just like with kinematics, this is going to be just before it hits the ground, not after the ground stops it. Because the ground, like the effectively the normal force, is effectively going to dissipate the thing into heat and sound. So we know that this is 0, but we still don't know what the velocity is there. Now, the idea here is that if you were to do this, and I'll do this with kinematics, and tomorrow we'll come back and revisit this problem with conservation of energy. And you might be able to kind of pick up on what's going to do it. Okay, so the initial, so we'll call this 1, 2, 3. So U1, U sub G1, no big deal. It's just, again, MGH. And the U sub G's are actually quite easy to calculate here. So it's 0.21, and then I'll just use 10 for G and then 4 for that. So it would be 2.1 times 4, which is going to be 8.4 joules. Great. Now, the kinetic energy is going to be 1/2 mv squared. And V in this case was 0, so kinetic energy, so K1 is just going to be 0 joules. Okay, cool. So then let's go to U sub G2. Well, it's going to be mgh. This time the m is the same, 0.21. The g is the same, 10, but now h is going to be 2. So this thing, it looks like a 5. That really should be a J. So this time it will be 4.2 J. Now, again, when we find kinetic energy, it can be a little tricky here. So what I would do is I would say, okay, I want this final velocity. So if I'm going to do this kinematically, it'd be 2a delta y plus v naught squared. Well, the v naught squared goes to 0, so the final velocity is just the square root of 2 times negative 10, because that's g in this case, times delta y, which was negative 2. So this would be the square root of 40. It looks like. Unless I have made a mistake, which I don't think I have. Be plus or minus, so it would be negative, but all right. Actually, I'll tell you what, we could find the final velocity, but turns out we don't need to. Final velocity squared is just as good for us because we want to find kinetic energy, which is 1/2 m times the velocity, the final velocity squared. So finding the final velocity squared is just fine for us. So that would be 2 times negative 10 times negative 2 because it went down. So this would end up being 40. And again, we could take the square root, but when we found the kinetic energy, we'd just be squaring it again. So then this is just 1/2 times 0.21 times 40. That is going to be 20 times 0.21, which would be 4.2 in the kinetic energy. So K2 ends up being 4.2 joules. Now, the idea here for U sub G3, this is going to just be mgh, but this time h is 0, so it's just 0 joules. And you might guess that, oh, I did not find total mechanical energy. The total mechanical energy here, so E1 was just UG1 plus K1, which would just be 8.4 joules. E2 is going to be UG2 plus K2, which would just be 4.2 plus 4.2 is 8.4 joules. Now, you might guess that E3 will also be 8.4 joules. And if you do, you're anticipating the conservation of energy, conservation of mechanical energy. But if we do V final 3 squared, this is going to be, again, 2a delta y, where this time delta y would be negative 4. So it would be 2 times negative 10 times negative 4, which would be 80. And then your k is going to be 1/2 mv squared. So this will be 1/2 times 0.21 times 80. And from that, you do, in fact, get 8.4 joules. So your K3 is equal to 8.4 joules. And that means each time your total mechanical energy stayed the same. So if this is the only thing that's going on, if all that's happening, if the only forces are conservative, and in this case, gravity is a conservative force, then all that's going to happen is you're going to get conversions between these forms of mechanical energy. Okay. And like I say, I want to devote a longer lecture to that because that is the primary tool that you're going to use to find the to solve the problems with this. But that's basically what's going on. Okay. Last thing I want to talk about today is power. And what power is a rate of energy use, generation, or transfer. Okay. Now, for an example of something that uses power at a certain rate, this would be like a light bulb. And if you've looked at the rating of a light bulb, it's given in watts, and watts is the unit of power. So I'll put that over here. Unit. It's going to be energy, some sort of energy divided by a delta time, which would mean it would be a joule per second in SI. Now, 1 watt is equal to 1 joule per second. So the symbol for that is 1 watt, 1 joule per second. Okay, so that is the units of power. So when you're talking about a 60-watt light bulb, what it's saying is it's saying this light bulb uses 60 joules per second. Okay, that's what's going on with that. Now, if you're talking about generation of energy, strictly speaking, energy is only converted. It's not created out of nothing. But in the context of that we're dealing with, we can talk about a battery as generating energy. Okay. And the idea is what's happening is the battery is taking some of the chemical energy it has in it. It's converting that to electrical energy, and probably some portion of the machine is converting that electrical energy into probably kinetic energy. So we might say that the battery is generating energy at 2 or 3 watts or something. Batteries they're not super powerful. You can make them powerful, but in general they're much better ways to generate power. Now, if we were to have something like transfer, an example of this would be like a turbine, where you can sometimes think about that as being a power generation, but you could also take into account that the moving water or moving steam has its own kinetic energy. Okay. And that motion is what's being transferred into the motion of the turbine. Okay. And ultimately into the electrical generation. So that is something that you could have. And you can measure all of these energy rates, these rates of energy, usage, generation, transfer. You can measure them all in watts. Okay. So that's the idea. And again, the general formula that you will use is you will use delta E over delta T. So it's some change in energy or energy usage, energy gained, energy transferred. You could also have work over delta T. This is another one that is sometimes used. And then the units are just going to be in watts. Okay. Now, one unit that you may, if you've paid an energy bill before, that you may have heard of is called a kilowatt hour. And really, people think about power, but really what this is a unit of energy, and we'll talk about this. Just want to talk about it right now. So 1 kilowatt hour, basically what this would mean is 1 kilowatt times hour. Okay. Now, what you can do is basically you can convert this. Instead of kilowatt hours, it would be 1,000 watt times hours. Or you can do, and then you can convert the hours to seconds by doing 3,600 seconds per hour. So basically what you get is you get 3.6 times 10 to the 6th watt seconds. Okay, that's what that is. Now, remember, a watt is equal to a joule per second. So this is 3.6 times 10 to the 6th joules per second times seconds. The seconds will cancel. So 1 kilowatt hour is 3.6 times 10 to the 6 joules. So it's 3.6 million joules. Now, why don't they just give you your energy rating in joules instead of kilowatt hours? Well, kilowatt hours is a lot of times more useful to you in terms of gauging, or it's more useful to think about in terms of gauging energy usage, because you don't really think about how many joules you use when you're using a tool. You think about, okay, or a device. You think about, okay, or you would say, okay, this tool uses energy at this rate. How much total energy you use is, of course, going to depend on how long you use it. Okay, so basically what a kilowatt hour is, it's the amount of energy you use up if you operate 1 kilowatt worth of electronic devices for an hour. Okay, and that is basically the unit of energy that is a little bit more graspable, because people can look at their devices and they can say, okay, this is rated for, how many ever kilowatts. From there, if you were so inclined, you could figure out, okay, how many kilowatts do all the devices in your house use? And then you could say, okay, roughly how many hours are we using these? And then from there, you could estimate, okay, how many kilowatt hours are we going to use? And then you generally get charged by the kilowatt hour. Okay, so that is another unit that's worth discussing with power. Next lecture, what we will do is we will go over the conservation of energy and then a few example problems as well. So I'm going to end things there. Thank you for joining me today. I will see you next time.